Okay, today is my last lecture of this course, and I'm going to briefly cover two topics which are both of which are quite interesting and deserves a separate lecture on itself, but since we are short of time, I think it's better to touch each of them, even though it will mean I'm not going to give any details. So these topics are a globalization procedure, globalization of Kontsevich product, and one application of this product, of this construction. Application which actually gives an important theorem, important result, which had been known before Kontsevich, but whose proof was quite complicated. But it turned out that Kontsevich's approach turns this construction into something pretty straightforward, although there is some trick involved eventually. Okay, so let's begin with the beginning. So last time when we met, I proved, at least I sketched the proof of Kontsevich formality theorem. Let me recall it. There exists, so let us consider manifold M equal just to a real affine space of arbitrary dimension, and let pi be an arbitrary Poisson vector on this space. Then, first, Kontsevich theorem claims that the Hochschild constant Rosenberg map pi from polyvector fields on Rd to polydifferential operators on the same space can be extended to an L-infinity quasi-isomorphism U, which is a collection of UN, and this map is from left to right, so UN is a map, roughly speaking, from the wedge product of n copies of the left hand side, although there should be some shifting. But I don't want to speak about this right now. To d star poly of Rd such that U1 is equal to the Hochschild constant Rosenberg map, and the usual equation I'll recall this in some time, a bit later, in a few minutes. And the usual equation on UN holds. And it follows from this claim that at the space, the sets of Marokatan elements on the left and on the right are isomorphic. Isomorphism is established by the application of this an infinity quasi-isomorphism U. In particular, every Poisson bivector chi every Poisson bivector pi, which is a Marokatan element on the left, induces the Marokatan element U of pi in the right-hand side of our map. And as I explained, Marokatan elements in the space of Pauli differential operators are responsible for the star products in RD, and hence the star product. As you see, this theorem concerns only local situation, that is to say, if you consider generic Poisson manifold M with Poisson bivector pi, and locally M is diffeomorphic to RD, equipped with certain Poisson bivector. So locally we always have the star product. So the first question which we should address is the globalization procedure, whether it is possible to go from locally defined star product to globally defined star product. And more generally, whether we can go from locally defined formality morphism U to globally defined formality morphism. Both questions have positive answers, and both. Well, I mean, of course, the formality, the star product, existence of star product would follow from the existence of global formality. So the second question is actually follows from the first. Well, the second part follows from the first part, and this first part appeared as a brief observation, not very brief, but just a couple of pages long observation in Kontsevich's original paper in 1997. He, in a very brief terms, he explained how this globalization procedure should go and why it actually always possible to globalize the formality morphism. This was very brief. This explanation has been very brief. So, as it is usual with Kontsevich's papers, this paper caused a flow of subsequent papers by various authors who tried to expand and explain Kontsevich's brief ideas. Among these papers you can mention papers by Dolgushev, papers by Kalak, papers by Shoichet, but I'm going to answer the globalization. I'm going just to very briefly describe Kontsevich's own ideas here, because they are worth being known first, and second, because in any case I don't have enough time to go deep into details of this globalization procedure. So let us speak briefly about the globalization of formality morphism first, or the formality morphism first. So first of all, we observe. So let's make the first step together. So first of all, we observe that formality morphism, Kontsevich introduced, can be applied in a word-for-word manner to not just to the space of functions or space of polyvector fields on Rd, but to space of polyvector fields of what they can call Rd formal. So what is Rd formal? It is a general idea in algebraic geometry nowadays that every space is characterized by its set of functions, by its algebra of functions. So when we speak about Rd, we usually consider either just smooth functions, or more often, at least in algebraic geometry, we restrict ourselves to the consideration of polynomial functions. And when we speak about formal Rd, it means that we actually replace polynomials by formal power series in n variables. So we can think of these variables x1 through xd as being local coordinates in the neighborhood of 0 at 0 at the origin in Rd. So you consider, when you consider formal power series in variables x1 through xd, you can say that you can actually consider Taylor decompositions, Taylor series associated with every smooth functions. There is a large theory behind this. There is Borel theorem, which claims that every formal power series can be identified with certain class of functions at the 0 at the origin of Rd. So that's not all very void. This theory is not void. This theory is actually quite important, and it has some relation to analysis. But for us, it is sufficient just to consider formal power series in the variables, and then it is natural to consider polyvector fields, with coefficients in formal power series. And of course, all the constructions we applied to usual polyvector fields go in word-for-word manner, can be applied in a word-for-word manner to this situation, and this gives us the formality morphism U from polyvector fields to polydifferential operators on the same Rd formal. Now, if we have a manifold M, a generic manifold M, And when we have a generic manifold and a generic coordinate system on M, we can apply this construction to the functions on M, well, localized, so to say, at any point, at the point where this generic coordinate system has the origin. I mean, say 0, 0, 0, 0 will correspond to point P in M. Then this formal power series can be identified with the classes of functions at this point, so-called infinite jets of functions. And we can go on. So we have kind of formality theorem, formality for the jet bundle of M. I'm not going to speak about jet bundle, so if you are familiar with this concept, then it's okay. If not, you can just imagine that you have local coordinates and you have formal power series at the origin, localized at the origin of this local coordinate system. It is not sufficient for our purposes to consider just the usual coordinate systems, because it's not enough of them. But on the other hand, when we consider just formal power series without convergence conditions, it enables us, it gives us more freedom to choose coordinate systems as well. Thus, we can, instead of usual coordinate system, consider so-called formal coordinate system. So, to understand this, let me recall that a coordinate system is a local diffeomorphism phi from a neighborhood of the origin in RD into M, so that 0, the origin, goes to the point P. Now we can consider classes of such local diffeomorphisms. So to say, we will say that two diffeomorphisms, phi and phi bar, are equivalent if their formal decomposition in infinite Taylor series at the origin coincide. I mean, phi of 0 should of course be equal to phi bar of 0, should be equal to P. If their Taylor series in the origin coincide. This gives us the notion of formal coordinate system. Formal coordinate system at a point P is at P is a class of equivalence. Okay, probably equivalence class, probably an equivalence class of diffeomorphisms at this point. A space of formal coordinate systems constitute a principal bundle over M, where the map is just given by forgetting the corresponding coordinate system and just sending every coordinate system at P to P itself. The fiber of this map is the space of formal diffeomorphisms of RD at the origin. So we have an infinite dimensional fiber bundle over M. Of course, for every, that's probably step 2 for us. Step 2. For every point P and the class of diffeomorphism phi at this point, we have a choice of coordinates, formal coordinates x1, xd. And hence we have, by Kontsevich construction, well, the formal Kontsevich construction, we have a map U from T poly, star of RD formal to D star poly of RD formal. Now globalization would mean that we to globalize the formality morphism would just, would boil down to choosing a section of this projection of this fiber bundle, right? So we have a section of this fiber bundle, global section, some S, and would be able to pull down this formality morphism at every point, and this will give us a genuine formality morphism from T poly of M to D poly of M. It's like Fedotov's construction. Fedotov actually did the same thing just for the star products. He observed that the star product exists formally at every point because of Moyle formula. Then the only problem he had was the globalization, and to do this globalization one actually needs some kind of section of the fiber bundle. Unfortunately, this particular fiber bundle is not trivial, and it doesn't have a global section. Let's let. However, it turns out that we can modify this construction a little bit. Namely, we can consider not all formal diffeomorphism. We can assume that the linear part of this diffeomorphism phi, or the diffeomorphism here, is actually fixed. This would mean that we actually fix the affine coordinate system at the point and allow only higher correction terms in the diffeomorphism. So, we'll say that phi is equivalent to phi bar if, roughly speaking, if I'm not mistaken, if a difference, let me see, yeah, I think we actually need something like this. I don't remember the details, unfortunately. It's a pity, but details are actually not important here. If yeah, sorry. So instead of this fiber bundle, we'll consider the fiber bundle with the group structure group Difflo morphism of RD formal for quotient factored out by the action of GLN, GLD of R. So to say, we will quotient out the action of general linear group. Then it will turn out that this was the only non-trivial part of this fiber bundle. So after quoting out the action of the general linear group, I mean, of course, every linear diffeomorphism of RD involves a diffeomorphism of RD formal, and hence we can just consider this GLD as a subgroup in diffeomorphism. So we can quotient out the action of this group, and this will give us another fiber bundle, which is called the bundle of affine coordinate systems. Now this fiber bundle is in fact has global section. The only thing we need to do is to show that these formal morphisms induce some formal morphisms on the level of these affine, this space of these affine coordinate systems. And it can be done because of the good properties of Kontsevich formality morphism. It actually is equivariant with respect to the action of GLD, and not only this, it has some other nice properties, and this enables us to induce some formality morphisms not for usual genuine local coordinate systems at M, but actually for affine coordinate system. So to say that affine change of coordinates will not affect the formality morphism that Kontsevich introduced. So now we have this formality morphism at every fiber here, and we have the global section, and we use this global section to pull down the formality morphisms from here to here. And that's actually how Kontsevich himself explained globalization of formality, of his formality theorem. Of course, this is pretty sketchy. If you believe that Kontsevich explanations are anyway better, you are welcome, but to be honest, his paper was very sketchy as well, and that's how it came up that shortly after the publication of this paper, there appeared lots of other papers explaining and modifying his construction. So that's probably step 3, but it doesn't matter. On the other hand, so of course, when we have global formality morphism like this, and we have a bivector pi here, we can define the global star product operation B on the right-hand side as well, just by using the same formula. However, if we are just interested in the star product, we would have avoided all this fuss with local coordinate systems and the affine coordinate systems, and also proving that this affine coordinate systems bundle allows a global section, which is non-trivial but a well-known result in the formal geometry. I think it was due to Gelfand and some of his collaborators in 1980s. and go straight to the point. So if we are just interested in star product, so if we are just interested in globalizing the star product, then we could have saved enough time by going straight to the point at the very beginning. So, I mean, as soon as we define the jet bundle and infinite jets of functions, as I explained, we identify two functions at a point if their Taylor decompositions at this point coincide. Right, so if I have infinite jets of functions on M at the point P, so we can identify it with the space of formal power series, in D variables. And use Kontsevich construction to induce the star product on these formal jets. Infinite jets. This gives us the algebraic structure on the jet bundle. So the jet bundle, infinite jet bundle of M. This is just the union of all P in M of the infinite jets at the points of M. It gives us the structure of fiber-wise algebra bundle on the infinite jet bundle. It is very similar to Fedosov's construction. So in Fedosov's case, we had Weil algebra bundle. The algebra bundle over M induced where the star product in every fiber was induced by the restriction of symplectic form at this fiber. So something like this can be applied, can be done here. Of course, one needs to be careful as to the invariant of the star product you obtain in that way, but this can be done. I just skipping lots of details here. And then Fedosov's construction induced. Well, Fedosov's construction involved was based on the existence of certain flat connection. On this Weil algebra bundle, which allowed us to identify the space of smooth functions on M with the space of flat sections of this bundle, and hence this way we'll get a non-commutative star product on the space of functions. So something like this can be done here. Actually, one can define an analog of Fedosov Fields of connection on this bundle with respect to the product induced from Kontsevich theorem, and the construction is pretty much the same as in Fedosov's case, in the symplectic case. You depart from the usual symmetric connection on your tangent bundle, and then, or T star, I don't remember, doesn't matter much because it's the same, of course. And then you modify it by adding terms by adding the sections, commutators with sections of this vector bundle. The only problem is that if you begin with a symmetric connection on T star M, it need not differentiate the star products in this bundle. So to make sure that it differentiates the star product, even though it is not flat, you need to add to this bundle a term which would look something like this: 1 over p factorial, I believe, u p plus 1 h bar to the power p. Here you have operator nabla, which you regard as a probably better like this. We have a vector field. So every connection is a differentiation of the section with respect to the vector fields on the base. So if psi is a vector field on the base, and nabla psi is the original connection, and then you modify this by using the formality morphism. At every, actually you do this fiber-wise, so you don't care about the global local properties of UP. Right, and then it gives you the differentiation of j infinity of m, and beginning with this you can do the standard trick of Fedosov to get flat connection out of this. So that's a method introduced by 3 Italian authors: Cataneo, Felder, and Tomasini. I think it's with 2M and 2S. Difficult to remember Italian names, sorry. It's interesting because it actually shows the close relation between globalization of Kontsevich construction and Fedosov's ideas. This approach was further developed by various authors who actually modified Kontsevich's original globalization of formality result in this way. So their construction was not, it was more abstract, it was more general, it didn't rely so much on the properties of the concrete formality morphism, because as I think I explained this. If I haven't, then I'm sorry. I think I explained that actually there exists more than just one formality morphism. Kontsevich's choice of formality morphism was a very special choice. It has lots of additional properties which can be used to obtain new constructions. So the authors who followed Kontsevich made this globalization procedure much less dependent on the choice of formality morphism, and they also used philosophers' construction, and that allowed them to obtain some results as to formality with certain restrictions. Like you can restrict the set of vector fields, the set of polyvector fields, and so on. But okay, let's go further. As far as the authors of these papers are concerned, they are Vasily Dolgushev, Damien Kalak. Also was a paper, there was a series of papers of Kalak together with Michael van den Berg. There were papers by Boris Shoichet, and so on and so forth. So there are lots of authors who can be mentioned here. Okay, let's go on and speak a little bit about the applications of Kontsevich formality theorem to something else rather than to the deformation quantization itself. To this end, let us consider the particular case when the manifold M is given by the dual space of Lie algebra. Let me recall that such spaces are always endowed with a canonical Poisson structure called sometimes the Kirillov-Koston-Suriot structure, or KKS structure. Roughly speaking, to obtain this structure, you need to identify elements of G with coordinates functions. On M, and so in order to obtain the Poisson bracket, it is sufficient to define the Poisson bracket of coordinates, and we just put that this bracket is given by the Lie bracket in G. If you choose local, so it means that, well, if you choose bases x1 through xn in G, then you can write down the Lie brackets in terms of the structure constants ci, j, k, xk. And if you now regard xi, xj, and xk as coordinate functions on G hat, or G check, sorry, then it would mean that the bivector, the kks bivector, is linear. It follows immediately that Kontsevich's construction induces a star product not just on the space of smooth functions on G check, but also on the space of polynomial functions of G check. It is easy to see this because if you remember UN, first of all, let me recall that the star product of F and G is given by the formal power series of this form, F times G plus H bar divided by 2 F comma G, and sum over K from 2 to infinity, H bar to the power K, I by K factorial, sorry, without K factorial sometimes, let's remove the K factorial, BK F G, and BK is the sum of all graphs gamma which has 2 points on the boundary, and K points inside in the upper half plane of weight attributed to this graph times the operator which you attribute to the same graph. This operator consists of certain compositions by vector pi. Roughly speaking, it is obtained like this. You put f and g in the points of the boundary, then you draw a picture where every point where there are k points in the upper half plane, and every point has two arrows that exit these 2 points. This is one of the possible pictures that you can draw. However, since pi, which stands here, or probably beta pi ij, the coefficient of the bivector that stands at every node of this graph, at every vertex of this graph, is no more than linear, and the arrow that enters this point denotes a differentiation with respect to a certain direction. It means that no more than one arrow can enter every point in the upper half plane. So altogether, there are 2 times k arrows in the graph gamma, and no more than k of them can go into a point in the upper half plane, can enter points in H. So it gives us k, or no less than k, arrows remaining that should go into f and g. Thus, the degree of the separated bk, the degree of bk, total degree, is greater or equal to k. And hence, if f and g are polynomials of total degree no more than k, all the terms starting with bk will vanish. Hence, we conclude that Kontsevich star product induces a star product in an algebra of polynomial functions on G. Algebra of polynomial functions on G can be identified with the space of symmetric tensors in G. The algebra of polynomial functions on G hat, G check, can be identified with this. And we see that now we can put h bar equal to 1 and obtain a star product in SG. On the other hand, since the first term here is given by the Poisson bracket, we conclude that the first term of this product is given by the star product it means that if we take x and y from G itself, of course G is a subspace in SG, right? So if you take this, then consider then by straightforward inspection of definitions, using this observation as well, we see that the commutator of x and y in the sense of the star product is given by just the Poisson bracket itself. To this end, you also need to observe that B2 is symmetric. B2 operator is symmetric, but yeah, let's skip it for a while. It's not hard to see. Hence, by the universal property of UG, I have a map, a homomorphism UG into SG equipped with this star product. And by comparing the sizes on the left and on the right, so here we use the Poincare-Hall-Beat theorem, and here we just use the fact that we know the size of SG. And also, since we know that both the left and the right-hand side are generated by G, generates both sides, we can conclude that UG is in fact isomorphic to SG equipped with this star product. So this gives us, by the way, a new method of proving the Poincare-Hall-Beat theorem. Well, I don't want to give details here, because it is much more important that this construction actually allows you to reproduce the famous Dufflo theorem. Let me explain what this Dufflo theorem means. To this end, let me recall that the Poisson center of any, well, I don't know, C infinity of M consists of all functions in M in C infinity of M, such that the Poisson bracket of F with anything vanishes identically. In particular, it is easy to describe the Poisson bracket of SG with respect to the KKS by vector. Namely, since SG is generated by G, an element is in the center if and only if it commutes with every element from G. On the other hand, this commutation amounts to the joint action of x on the function f. I hope you are familiar with the basic ideas from Lie theory, and you are familiar with the notion of a joint action. So this action is trivial if and only if the larger joint action of any element G in the group G associated with Lie algebra on F is trivial. Thus we can identify this space as a space of adjoint invariant functions, polynomials on G. Similarly, one can describe the center of universal enveloping algebra the center, in the usual sense, center of an algebra, let me recall, the center of an algebra is the space of all elements A in A such that AX is equal to XA for all X in A. That's the center. Similarly, the center of the universal enveloping algebra in this sense will coincide with the space of G invariant elements in the universal enveloping algebra. That's also because the commutation of any element F in UG with an element X in G amounts to the joint action of X on F. Thus, since the symmetrization map sigma from SG to UG, the standard map used to prove the Poincare-Hopf theorem commutes with the action of the group. We conclude that symmetrization induces an isomorphism of centers Z pi of SG with Z of UG. However, this map, even when it is restricted to the invariant part of the symmetric algebra, is not a homomorphism of algebras. Not homomorphism. It's in other words, it doesn't send products on the left to the products on the right. Well, since we can always describe commutative algebras of this sort in terms of generators and relations, and it is known that on both sides algebras are free algebras, free commutative algebras with a fixed set of generators, it is always possible still to identify these algebras, these and these, as algebras. However, the isomorphism, well, will depend on the choice of generators. So it's been a long-standing problem whether it is possible to modify sigma so that sigma restricted to this new modified sigma restricted to the center will gives you an isomorphism of algebras. Dufflo's theorem actually gives you construction which allows one to do this. Let me very briefly describe this construction. So, Dufflo's construction. We begin with considering a map add from a joint representation map from G into the space of endomorphisms of G, which you can of course identify the space of complex valued matrices, complex or real doesn't matter, of size n capital, where n capital is the dimension of G, sorry. So this is a function. So you can regard this map as a matrix-valued function. Actually, a linear matrix-valued function on G. This space can be identified easily with G hat tensor with matrices. Right. Probably better to put linear here. I'll probably just home. Yeah. Okay. G check. So when you have functions, you can obtain other functions from them. Especially, I mean, here, of course, you have functions with values in some non-commutative algebra, but that is not a big problem for us. So let us consider the following expression. So SH stands for the hyperbolic sign. I think in international abbreviation for this is sin h. So let's consider the function sin h of s of x equal to sin h of x divided by 2, which we divide by x divided by 2. You remember that sin h, the hyperbolic sign, is represented by a formal power series, not actually by the formal, by convergent power series, which starts with x, right? Sin h of x is x plus, I believe it should be, what was it? Could never remember this. Yeah, yeah, it should be something like x cubed divided by 6, I think. Yeah, and so on. In general, it should be x5 divided by 5 factorial and so on. Right? So you can divide it by x formally, and that gives you a formal power series on the left. Then, if you're familiar with formal power series, you know that you can do lots of tricks with them. So the first trick we're going to do is to consider S of add as a function, matrix valued function, formal power series, matrix valued formal power series on G hat with coefficients in matrix, right? Matrices. So it's formal power series, so let me use hat to distinguish polynomials from formal power series. Now you can take the determinant of this, and this will give you a formal power series just like this without matrices. And then you take the square root of this construction. And now denote this as J. J of x. X is an element in G, right? Yeah. So this is again an element here. Okay. Now you can identify G hat with a space of partial derivatives on derivatives on SG. Hence, Jx will become a differential operator, formal differential operator of infinite degree, of course. But when you apply this formal differential operator to a polynomial, an element of SG, you'll always obtain a finite sum of elements. And we eventually come up with the following result, which is called Dufflo's formula, Dufflo's theorem. Consider the map J from SG to universal development algebra given by the following composition. G is equal to G of F. It should be equal to the symmetrization of J of X applied to F. Then J is in fact a homomorphism, and actually an isomorphism on the level of centers. So J restricted to the center is an isomorphism of algebras. The original proof by Dufflo was rather complicated and involved, so I'm not going to talk about this. I'm going to give a very brief outline of Kontsevich's construction. It actually reproduces Dufflo's result and is based on his interpretation of universal development algebra as the algebra of polynomials with respect to the star product. So let me first prove the following proposition. Suppose pi is an element in the Markov set of T poly. I'm going to put anything here. B is given by the Kontsevich map applied to pi. Let me recall that this is given by the formal power series from I from 1 to infinity. Okay, k 1 over k factorial h bar to the power k u k of pi comma pi comma pi. Then for every element f in the Poisson center of C infinity of m, this m is what we have here, with respect to the Poisson by vector pi, the map u1 sub pi of f given by the formal power series h bar to the power k divided by k factorial uk plus 1 f pi comma pi is in the center of the algebra of functions on M with respect to the star product. The proof is pretty straightforward, and I'm afraid I'm running out of time, so I'll probably skip some computational details. But still, the idea is very simple. It resembles the proof of the fact that B of phi is in fact the Markatan element, wherever pi is Markatan element. So to prove this, we observe that F is the Poisson center of this algebra if and only if the Lichnerovich-Poisson differential of F, which is just this Houghton bracket of pi and F, vanishes identically. Similarly, some F capital is in the center of the algebra of deformation quantization, that is the algebra of functions with respect to the star product, if and only if the following equation holds: delta of F, which is Hochschild homology, Hochschild differential, plus the Poisson, the Gerstenhaber bracket of B and F capital vanishes identically. In fact, you can forget about the first term here, because this first term vanishes since F has degree 0, F is a function. Hence its Hochschild differential vanishes. And just look at the second term, and then this is precisely the condition that B, F, comma G vanishes, but B, F, comma G is equal to F star G minus G star F. So if this vanishes, then this vanishes for all G, right? And vice versa. So this is a very straightforward observation. Now, to prove that U1 sub pi of F verifies this equation, so delta of U sub pi 1 of F plus B of F U pi sub 1 of F verifies this equation, can be proved by straightforward computation from the definition of the L infinity morphism. In fact, you can actually replace F with arbitrary polyvector pi p here, right? In that case, the left-hand side will not necessarily disappear. And then you can just use, I'm not going to write this, but let me just recall that the following is true, that delta UK applied to P1 PK is equal to a sum plus or minus UK minus 1 PI PJ and everything the rest. So the sum is taken for all I less than j plus a sum, again with certain signs, of U P U1 u sigma of 1, u sigma of p, sorry, not u, p, sigma of p, uq, p sigma of p plus 1, p sigma of n. Now the sum is taken over all p plus q equal to n, and to k, and all shuffles sigma of p and q elements. Okay, so that's more or less a straightforward thing. Now it only remains to show that u pi 1 of f times g, where f and g are elements in the Poisson center of Sg, will be equal to u1 pi of f, u1 pi of g. Well, to this end, we need to, well, this is probably the most subtle part of Kontsevich's proof, and he only gives a very brief outline, barely more than just a bare idea. So let me repeat this argument. First of all, let us observe that we can actually can actually define the cup product of two polyvectors, wedge product of two polyvectors, E wedge Q, as the differential operator associated with a certain graph gamma and certain weight, which I'm not going to speak about right now, applied to P and Q precisely in the way it is done in Kontsevich's quantization. Namely, this gamma should consist of just P plus Q points on the boundary of the upper half plane and two unrelated points in the half plane itself. The first point will correspond to the bivector, to polyvector P, and the second point will correspond to polyvector Q. So directly from the definitions that Kontsevich gave, it followed that this operator, this on the right hand side, is precisely equal to this. This allows us to consider to consider the operators, consider the graphs corresponding to u1 pi of p wedge q, which is, let me recall you, equal to the sum with certain coefficients and graphs corresponding to u1 pi of p cup product with u pi 1 of q, right? So these graphs are easy to draw. For instance, in the first case, we'll have so originally there should be k plus 1 points in the upper half plane plus certain number of points on the boundary, precisely as many as is the degree of p times q. So I don't care about the points on the boundary at all, but now I will break down the point that will correspond to p wedge q into 2 points very close to each other. One will correspond to p, the other one will correspond to q. Now there are certain elements here where they merge, where they go, and there are some points p, some points with 2 arrows exiting from them that contain the bivector. These points can be drawn in a pretty arbitrary way. The only question is that these 2 points should be infinitesimally close to each other, so that the distance from them compared to the from one of them to the other one will be much smaller than the distance from each of them, from either of them, to the points represented by vector pi. So that is the first of these graphs. The second graph will correspond to something like this. You'll have one point corresponding to p, which is very close to the boundary, right? And which is, well, acted on by some bivectors. So it's very close to the boundary, so it corresponds to this, right? And another point which will correspond to q, which will also be very close to the boundary, but they should be pretty far away from each other, right? So now the only thing we need to observe is that these 2 pictures are actually homotopic. The homotopy is given by naive move, which sends the point that corresponds to p and q on the bottom picture to the points that correspond to p and q on the top picture. Hence, these 2 maps are homotopic, and that means that the corresponding products are chain homotopic. So the chain homotopy should be given by differential operators, by Hochschild differentials and differentials involving the star product as well. I don't care much. So it's something like this. It's some u2 tilde pi delta u2 tilde pi of p comma q minus u tilde pi 2 of d pi p q plus minus u2 tilde pi p d pi q. And now, if we, instead of p and q arbitrary polyvectors, you plug into this formula f and g, then you will see that the right-hand side will vanish identically. The first term will vanish because of the dimension count. It falls into the space which is 0, which is just identically equal to 0. And the 2 remaining terms will vanish because d pi of f and d pi of g are both 0. So it means that the map u pi 1 induces a homomorphism of algebras on the level of centers. From the center, Poisson center of SG into the Poisson center, into the usual center of U. And, well, it is not yet clear that this map coincides with Dufflo's map, but this can be proved, and that's what Kontsevich does. By some trick, of course, but I think it's still not enough time to speak about this. I think it's time to stop here.